Fuel feedback systems are used on some 4- and 6-cylinder AMC and Jeep vehicles. 4-cylinder models utilize a fuel feedback system that varies somewhat in design from the 6-cylinder system. Both systems help reduce the emission of harmful pollutants through the exhaust system by controlling the air-fuel mixture introduced into the engine. In this film, we'll answer these questions. First, what is a fuel feedback system? Why is it needed? How do the 4- and 6-cylinder systems operate? It's important that you understand fuel feedback theory of operation so that you'll be able to test and service these systems in the future. The reference book that accompanies this film provides you with the procedures you'll need to diagnose and repair these new systems. Now, what exactly is a fuel feedback system? A fuel feedback system is an emission control system that uses an electronic signal generated by an exhaust gas sensor to control the carburetor air-fuel mixture ratio. As you can see here, there are a number of components involved in this process. In each of our systems, an oxygen sensor located in the exhaust stream gauges the amount of oxygen present in the exhaust gases. The sensor sends an electrical signal to an electronic control unit. This signal varies with the percentage of oxygen present in the exhaust gases. The 6-cylinder system's electronic control unit is called the MCU. The unit utilized in the 4-cylinder system is the ECM. These units convert the signal received from the oxygen sensor into electrical impulses. In addition to the signal received from the oxygen sensor, the control units also receive input from other sources. Each system utilizes a coolant temperature sensor. These sensors provide the systems with input regarding engine temperature. In the 6-cylinder system, the sensor activates a vacuum switch. In the 4-cylinder system, the sensor provides input directly to an electronic control unit. The 6-cylinder system uses 3 vacuum switches, which provide the control unit with engine operating information. The 4-cylinder system uses only 2 vacuum switches, which provide idle and wide-open throttle information to the control unit. The electronic control units, in response to the various input, send electrical impulses to the mixture control devices shown here. In the 6-cylinder system, a stepper motor varies the air and the air-fuel mixture by moving air metering pins in the carburetor. In the 4-cylinder system, a mixture control solenoid varies the amount of fuel in the mixture by controlling fuel flow to the carburetor's idle and main metering circuits. Now that we know what fuel feedback is and what the components of our system look like, you're probably asking yourself this question: why is fuel feedback needed anyway? To answer this question, let's take a quick look at how the air-fuel mixture affects exhaust emissions. There are 3 types of harmful pollutants present in the exhaust gases of any internal combustion engine that operates on gasoline. The unburned hydrocarbons, which are depicted here, are the first type. The second type of pollutant is carbon monoxide gas, which is created whenever gasoline is burned. The last type of pollutant is the group of gases called nitrogen oxide, or NOx gases. These gases are also formed by the combustion process. In addition to the 3 potentially harmful emissions we've seen, a combustion engine also emits 2 harmless emissions: water vapor and carbon dioxide. Even though these 2 emissions aren't pollutants, they're important to our discussion. They're important because hydrocarbon and carbon monoxide emissions are eliminated by converting them into these harmless gases before they leave the vehicle. For a more in-depth explanation of emissions theory, be sure to refer to Training Release 79-5, Emission Controls Part 1. Training Release 79-6, Emission Controls Part 2, explains all of the AMC and Jeep emissions control systems. If you haven't viewed these emission control training films, be sure to do so. This will make it much easier for you to grasp the theory behind fuel feedback. In addition to the emission control systems, there's another effective way to reduce the emission of the harmful pollutants. By maintaining a precise air-fuel ratio, a maximum number of hydrocarbons can be consumed in the combustion process, while minimal amounts of carbon monoxide and NOx gas are created. This graph shows how hydrocarbon emissions are affected by various ratios. As you can see, a 16:1 setting holds hydrocarbon emissions to a minimum. Carbon monoxide levels, just like hydrocarbon emissions, decrease as the air-fuel mixture is leaned out to about a 16:1 setting. But nitrogen oxide emissions really throw a monkey wrench into the works. At a 16:1 ratio, where hydrocarbon and carbon monoxide emissions are kept to a minimum, NOx emissions are at their peak. The trick is to establish a particular air-fuel mixture that delivers the best of all worlds. Here, at a precisely controlled 14.7:1 setting, we're keeping all of the emission levels to a minimum. There is one more very major consideration that makes a fuel feedback system so desirable. For several years, our vehicles have utilized the two-way catalytic converter shown here. This is called a two-way converter because it converts only two of the pollutants, hydrocarbons and carbon monoxide, into water vapor and carbon dioxide. It has no effect whatsoever on NOx gases. A new dual bed converter is used in conjunction with the six-cylinder fuel feedback system. This converter, which contains two honeycomb beds, treats nitrogen oxides as well as hydrocarbons and carbon monoxide. The front bed contains rhodium, the substance that's responsible for converting the NOx gases. The rear section contains palladium and platinum, the catalysts that convert the hydrocarbons and carbon monoxide. The blue arrows here represent fresh air, which is piped from the vehicle's air injection system into the rear section of the converter. This fresh air aids the conversion process for the hydrocarbons and carbon monoxide. The converter used with the four-cylinder fuel feedback system also treats all three harmful pollutants. As you can see here, though, this is a pellet-type converter. In order for these new converters to treat all three pollutants, the air-fuel mixture must be precisely controlled. The oxygen level in the exhaust gases tells the fuel feedback system what mixture the engine is operating on. As shown here, a leaner mixture produces more oxygen than a rich mixture. Oxygen sensors are used to gauge the level of oxygen present in the exhaust gases. Based on the input from the sensor, the control unit can effectively vary the air-fuel mixture. To summarize, these are the reasons why a precisely controlled air-fuel mixture is so desirable. First, the right mixture limits the formation of pollutants during the combustion process. And secondly, a precise mixture guarantees a precise level of pollutants in the exhaust gases. This precise level facilitates the use of the three-way catalytic converter. Now let's see how the fuel feedback system achieves this goal of maintaining a precise air-fuel ratio. As we've seen, the principal components of the six-cylinder system are the oxygen sensor, the MCU, the CTO switch, the three vacuum switches, the stepper motor, and the dual-bed catalytic converter. Another important element of this system is a tachometer input lead, which connects the ignition coil's minus terminal to the MCU. This tachometer input allows the MCU to vary its impulses with engine speed when necessary. So this is what the entire six-cylinder system looks like. Now, let's see how it functions. The oxygen sensor is threaded into the exhaust pipe directly in the exhaust gas stream. A shield is used to protect the fragile platinum electrode against damage from exhaust particles and handling. The sensor is sensitive to the presence of oxygen. As long as the temperature of the gases is over 660 degrees Fahrenheit, a voltage signal from the sensor is sent to the MCU. When the mixture is lean, a low voltage signal is produced. When the mixture is on the rich side, a higher voltage signal is sent. A mileage counter in line with the speedometer cable indicates when to replace the oxygen sensor. When 30,000 miles have elapsed, the counter actuates an instrument panel light. When you replace a sensor, you can reset the counter. The stepper motor moves the air metering pins in small increments or steps in response to the electrical impulses from the control unit. This is why it is called a stepper motor. Here, the metering pins are in the lean position. Here, the stepper motor has moved the pin about 50 steps because the oxygen sensor has determined that a somewhat richer mixture is required. This 50-step position is the midpoint of the metering pin's total travel. And this is the full rich position. Keep in mind, though, that in actual operation, the metering pin may be at any step between 0 and 100 in order to provide the correct amount of air. The fact that the system analyzes and adjusts the air-fuel ratio based on MCU evaluation of input signals is the source for the system's name. The system receives feedback on its effectiveness. In electronic terminology, this is referred to as closed-loop operation. Certain types of engine operation, such as engine warm-up, require that the fuel feedback system be bypassed. When the engine is cold, the MCU simply drives the metering pin to a predetermined rich position. Since this position is predetermined with no relative feedback to the results of this position, this type of operation is referred to as open loop. Another condition that requires an open loop mode is wide open throttle operation. When the driver opens the throttle all the way, the MCU drives the metering pins to a predetermined position. This position provides a proper mixture for acceleration. The system must also be in an open loop mode when the engine is idling. This condition requires that the MCU drive the metering pin to still another predetermined position. Since more than one of the open loop triggering conditions can be present at one time, the MCU is programmed with a priority ranking of operations. It obeys the input of highest priority. Engine warm-up is the highest priority condition, followed by wide open throttle, then idle speed. For example, if a cold engine was idling, the MCU would instruct the stepper motor to drive the metering pins to a predetermined position for engine warm-up, not its idle position. The vacuum-operated switches provide inputs to the MCU to trigger the open loop or closed loop functions. As you can see, these switches are color-coded to facilitate the operational tests provided in the film reference book. Remember, there's still another input source to the MCU. This is the tachometer input wire, which allows the MCU to vary its impulses with engine revolutions when necessary. Let's see how the system functions in its various modes. This is the initialization function, which begins as soon as the driver puts the ignition switch in the on position. The MCU sends an electrical signal to the stepper motor, instructing it to move the air metering pins to their full rich position. Then, the MCU instructs the stepper motor to move the metering pin back toward its lean position a predetermined number of steps. The metering pin stays in this position until the other input sources report to the MCU. When the engine starts, the yellow vacuum switch tells the MCU if the engine is cold. This vacuum switch receives manifold vacuum from the CTO switch. If coolant temperature is below 100 degrees Fahrenheit, the CTO switch passes vacuum to the yellow vacuum switch. Now the vacuum switch's electrical contacts close. This tells the MCU that the air metering pins must be moved to their predetermined position for a cold engine condition. When the coolant temperature warms to approximately 100 degrees, the CTO switch blocks the manifold vacuum signal to the yellow vacuum switch. The switch's contacts open, and the MCU shifts to closed-loop operation, unless other conditions exist that require open-loop operation. When the engine is run at wide-open throttle, the blue vacuum switch informs the MCU of this condition. As long as this switch receives a vacuum signal of at least 2.5 to 3.5 inches of vacuum, the switch's contacts remain open. But here, the manifold vacuum has dropped below this limit under full acceleration. The switch's contacts close, and the MCU sends a signal to the stepper motor, telling it to position the metering pins in its predetermined wide-open throttle position. The pink switch tells the MCU when the engine is idling, the last condition requiring open-loop operation. This switch operates on carburetor-ported vacuum which drops when the throttle plate closes at idle. Above idle, this switch's electrical contacts are in their open position. Here, the ported vacuum signal has dropped below a particular limit, causing the pink switch's contact to close. This triggers the open loop mode, and the metering pin is moved to its predetermined idle position. An additional function of the fuel feedback system is to improve drivability in response to various abnormal conditions. As the system shifts during closed-loop operation, the MCU notes the amount of movement the metering pin makes as well as the direction in which it's required to move. Repeated consistent movements will eventually cause the MCU to recalibrate all metering pin positions a similar amount. This function tailors mixture ratios to atmospheric conditions. The fuel feedback system used on four-cylinder vehicles sold in California utilizes essentially the same principles as the six-cylinder system. The chief design difference is that the four-cylinder system varies the amount of gasoline in the mixture. This system's components are the oxygen sensor, electronic control unit, mixture control solenoid, CTO switch, and two vacuum switches. The four-cylinder's oxygen sensor functions in exactly the same ways as the sensor used in the six-cylinder system. The only noticeable difference between the two is that the four-cylinder sensor's tip is more rounded. Also, this sensor is mounted in the exhaust manifold, whereas the six-cylinder sensor is located in the exhaust pipe. The four-cylinder's electronic control module is called the ECM. This unit is located in the right side of the passenger compartment. The ECM provides an electrical signal to the mixture control solenoid, which is shown here. This solenoid controls the fuel flow in the carburetor. Here's how the mixture control solenoid works. The solenoid actuates a spring-loaded metering rod, which controls fuel flow to the idle and main metering circuits of the carburetor. One terminal of the mixture control solenoid is connected to 12 volts, while the other terminal is connected to the ECM. The ECM, in response to various inputs, provides a ground path for the mixture control solenoid. Here, the ECM is not switched to ground, so the mixture control solenoid is de-energized. Now the solenoid is in its rich position. Note that the fuel is now flowing through both the main jet and the solenoid jet. In the on condition, the ECM is grounded. Now the mixture control solenoid is energized. This is the lean position. In this position, the fuel flows through the main jet only. In actual operation, the ECM is continually energizing and de-energizing the mixture control solenoid. The on-off action of the solenoid is termed the duty cycle. As is explained in the reference book, the duty cycle of the mixture control solenoid can be accurately measured with a dwell meter. Just as with the six-cylinder system, there are some engine operating conditions that require open-loop status. First, the four-cylinder system has a warm-up open-loop mode, as does the six-cylinder system. This system also has an open loop for wide-open acceleration. This is called the enrichment mode. The coolant temperature sensor sends the ECM information on engine temperature. This sensor is mounted in the cylinder head. These switches provide information to the ECM regarding throttle position. Both switches are mounted on the right front fender. When we looked at the six-cylinder, we saw an engine startup mode called initialization. In the four-cylinder system, this startup mode is called the INHIBIT mode. As the engine is cranked over, the tachometer input tells the ECM that engine speed is less than 200 RPMs. Under this condition, the ECM sends no signal to the mixture control solenoid. This provides a rich mixture, so the engine can be easily started. After the engine starts, the system must determine if closed-loop operation can begin or if the cold operation open-loop mode is required. Three inputs go to the ECM. First, the oxygen sensor temperature must be above 1100 degrees Fahrenheit. Secondly, coolant temperature must be above 176 degrees Fahrenheit. Thirdly, the ECM has an internal clock that determines if 2 minutes have elapsed since startup. This is important because the catalytic converter needs 2 minutes to warm up. If all of these conditions are not met, the ECM sends a fixed open-loop command to the mixture control solenoid. During heavy engine loads, the throttle is wide open. To maintain good performance, more fuel must be supplied for complete combustion. During wide-open throttle operation, manifold vacuum drops. This causes the contacts in the wide-open throttle switch to close. The ECM is grounded, and the system goes into open loop. The four-cylinder system has several adaptive modes. In these modes, the system modifies the loop during idle and part throttle deceleration. The ECM utilizes input from both vacuum switches and the tachometer lead. Essentially, the adaptive modes allow the system to react to conditions such as abrupt throttle position changes. Well, that's about it. To summarize, we've defined fuel feedback as an emission control system that uses an electronic signal generated by an exhaust gas sensor to control the carburetor air-fuel mixture. We've also discussed the reasons why a fuel feedback system is needed. And finally, we've discussed how the AMC Jeep systems function, both the six-cylinder system and the four-cylinder system. Be sure to hang on to your film reference book. It contains the testing, diagnosis, and repair procedures you'll need to service the fuel feedback systems. Remember that the technical service manual is your most comprehensive source of information on the fuel feedback systems.